Hello everyone, I want to pick up where we left off and talk about the next module, Module 9. Before I do that, I just want to mention that whenever I post these videos to YouTube, if there's anything that I say that is an error, I'm going to attempt to annotate that on the YouTube video after the fact. Unfortunately, YouTube got rid of the annotation feature, but I found a workaround by using the polling feature. So what you should do is pay attention to this upper right hand portion of the screen on the videos and take a look and see if you see any quote unquote previews to a poll there, because that will tell you essentially whatever comment I'm trying to make to correct any errors I may have said. Okay, so with that order of business out of the way, just wanted to say that since we've finished Module 8 and are ready for Module 9, we've effectively studied all the phenomena you're required to know for electricity and magnetism as separate things. And now I want to combine this knowledge together and discuss electromagnetic radiation, or what we can also call light. So what is electromagnetic radiation? Essentially, we're looking at waves of electric and magnetic fields that are oscillating in a way that is depicted here in this cartoon. Hopefully you can try and visualize. It's always hard to depict in 2 dimensions something 3-dimensional. But what's happening is that the electric field and the magnetic field are perpendicular to one another. So here you see the magnetic field oscillating in this plane that's supposed to be coming out of the page or out of the screen, and then this is the electric field oscillating up and down on the plane of the screen. Okay, so whenever a wave like this propagates, and if it's doing so through a vacuum, it will do so at a speed of 3 times 10 to the 8 meters per second, which is given the special value c because this is the speed of light. If the wave, the electromagnetic wave, has to travel through some other medium other than a vacuum, then its speed will be slower. Depending on that medium, some media will slow the light wave down faster than or more than other media, and we'll talk about that more when we start talking about refraction later on. Okay, so one thing that's interesting to note is, this may seem a little bit abstract other than me saying electric fields and magnetic fields and showing you a cartoon, but if you take these constants that we've been using all semester and you place them into this formula, so here is the permittivity of free space, and here is the permeability of free space. Then if you place them into this formula, basically you're multiplying them and taking the square root. 1 over that value will turn out to give you 3 times 10 to the 8 meters per second. And so this gives a theoretical basis for the speed of light. For a long time, people didn't necessarily believe that this would be a constant of nature, although it seemed to be built into the equations of electricity and magnetism. And it wasn't until 1887, Michelson-Morley did an experiment that essentially verified that this was true, experimentally verified that the speed of light was indeed a constant of nature. We don't really have time to go into that whole story, although it is an interesting story, so if you have time while you're learning online, you can Google that. In any case, any sort of wave, like other waves we may have studied, its speed can be found by multiplying the wavelength times the frequency, wavelength being lambda, frequency in this equation being f, and so the speed of light can be found by multiplying the light wave's wavelength times its frequency. In other words, there is a relationship between wavelength and frequency, whereby if I increase one, then the other is going to decrease so as to give me the same product, which is a constant of nature. So we can then look at the entire spectrum of possible wavelengths and frequencies that constitute the electromagnetic spectrum. What we see of that, the thing that we call light, is usually, we kind of intuitively mean visible light, but there's plenty of other light that we don't see. In fact, we're mostly blind to all the light that exists. You could think of it that way. The entire electromagnetic spectrum consists of electromagnetic radiation ranging from very low frequency or long wavelength radio waves all the way up to very high frequency or very short wavelength gamma rays and everything in between. So you might wonder, well, why is it that we see just this small little swath in the visible portion of the spectrum? Well, there's two answers to that question. Number one has to do with the fact that the star that we orbit, the sun, gives off light in many bands of frequencies, but if you take a look at how much the intensity is based on the frequency, this plot here shows you different temperature light sources and where how much light they give off at different frequencies. You could see that the peak for the curve that corresponds to something of the temperature of the surface of our sun is right here in the visible portion of the spectrum. But you might ask, well, why not be able to see that and everything else? There's still plenty of light given off by the sun in these other frequency ranges. Why not just be most adapted to this and not the other frequencies? And the answer to that has to do with the fact that not all those wavelengths or frequencies of light make it to our eyes very readily. The Earth's atmosphere and also water itself, where eyes are thought to have evolved, blocks out many frequencies of light that we cannot see in other wavelengths. And so it makes sense that our eyes would be most attuned to this window in the optical part of the spectrum, which consists of the colors of the rainbow, Roy G. Biv, from long wavelength to short wavelength. And so actually it's probably pretty good that the atmosphere of the Earth blocks out some of this high frequency radiation, because it turns out that energy is proportional to the frequency of light. And that means that the higher the energy, or the higher the frequency, the higher the energy. And you could imagine that with enough energy, this could be potentially harmful to living cells. But with that knowledge that the energy is proportional to the frequency, we can re-examine this electromagnetic spectrum in terms of energy. So what it's saying is that the electromagnetic radiation down here in the radio end of the spectrum is very low energy because its frequency is very low. Infrared is going to be slightly more energetic, okay, and frequency increases as we go right on this plot. So visible light will be higher in energy than infrared or radio. Ultraviolet will be even higher in energy. X-rays will be even higher in energy. And gamma rays will be the most energetic in this spectrum of light. So how much energy is potentially harmful? Energy is above 480,000 joules per mole can have the potential of breaking chemical bonds and thus be possibly carcinogenic. So we would prefer to not be exposed to energies above this 480,000 joules. And if you go back to the regions of the spectrum that I just pointed out, radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma ray, we can specify what sort of energies those correspond to, and you can see that this magic number, 480,000, occurs somewhere in the ultraviolet region of the spectrum. What that's saying then is anything more energetic or higher in frequency than ultraviolet, so anything basically from here and below, could be potentially harmful, and anything above this line should be safe. You kind of intuitively know that because you generally take precautions against these higher frequency forms of electromagnetic radiation, ultraviolets, X-rays, and gamma rays, either by some sort of a lead apron or even something as mundane as sunscreen to protect yourself from ultraviolet radiation. Humans generally take precautions and try to minimize their exposure to those kind of high frequency forms of radiation. On the other hand, you don't generally take precautions against any frequency of radiation from visible and below. You don't generally protect yourself and put sunscreen on if you're just reading from a desk lamp that's giving off only visible light, nor do you take precautions against, say, the infrared radiation that comes out of your hair dryer or the radio waves that are all around us at all times. That includes, by the way, the use of cell phones. There's a lot of worry out there that, especially with the move to 5G, that this low frequency radiation could be potentially harmful. But if you look at the energy consideration, it is less energetic than your hairdryer or your desk lamp. So those kind of worries seem to be ignoring this basis of energy consideration. Of course, energy may not be the only consideration. Perhaps we want to investigate the power, the intensity of the radiation that we're exposed to. And is it possible that this could be hazardous? It's a fair question. When we studied energy back in Physics 1, we also talked briefly about power, which was the rate at which energy was done. And so when we look at that in terms of light, essentially you're going to experience this power as brightness or intensity. By the way, intensity then is the power divided by the area that power spreads out throughout. So what kind of power is potentially harmful? Well, 100 watts per kilogram is what we would be looking at. Penetrative powers of that level could be potentially hazardous. So for comparison for you, to attach some other numbers for you, if you look at the power of a cellular tower, if you are 10 meters away from it, you're looking at 0.36 watts per kilogram, which is very small compared to this 100 watts per kilogram that we're worried about. If you're near a Wi-Fi router, 1 meter away from a Wi-Fi router, that's 0.0057 watts per kilogram, just a tiny, tiny fraction of even a watt per kilogram, let alone 100. And even if you have your cell phone a centimeter away from your brain, which might be the average thickness of a human skull, you're looking at 0.75 to 1.6 watts per kilogram. Again, not even, less than 1 to 1.5% of the intensity that would be potentially harmful. So basically, power, like energy, shows us that if we think about these things carefully, your cell phone is not something that you need to be concerned with. The power output produces about 1/1000th of the heating to your brain that would be caused by wearing a hat. So unless you're worried about cooking your brain when you wear a hat, or unless you're worried about the infrared radiation of your hairdryer potentially being carcinogenic, then there isn't really a reason to worry about cell phones being hazardous to your health. And that's my little public service announcement to unfounded fears that are not based upon science. All right, that finishes up this lecture, and I will see you again next lecture.